Homework questions?
Didn't have any.
Okay. Why didn't we have homework? All right. So today I just want to spend the day talking about the truss simplification. And this is a way to, let's say this drastically cuts down the number of variables and equations for certain types of structures. And the key concept for understanding this truss simplification is two force bodies. Okay, so if you have some random, it doesn't, we're usually going to think of these as straight, narrow members, but it doesn't matter what the shape of the body is. And say that you have a force here and a force here. Okay. And if this thing is in static equilibrium, let's think about the possibilities for these forces. Okay. So first of all, let's think about just two arbitrary forces. Okay. And let me make it clear that these are different magnitudes. Okay. These could not be in static equilibrium because these two forces don't add up to zero. Okay, so the center of mass of this thing would be accelerating. Okay. So first of all, the requirement that the center of mass doesn't accelerate well, if we're going to get the center of mass not to accelerate, those two forces have to cancel each other out. Okay, so the forces have to be equal and opposite. Okay, so you can't have a situation like this. Okay, but now I'm going to redraw one of these and think about a case where these forces are equal and opposite. Okay, so now imagine those two are equal and opposite. Would this be in static equilibrium?
Almost.
Well, the center of mass would not accelerate, but this thing would spin. So the requirement that the body doesn't rotate. Well, what would that require? We need the couple to be zero from these, right? These equal and opposite forces in general produce a couple. We need that couple to be zero. And so what would it require for these two forces not to produce a couple?
They need to be in line with each other.
Yeah, they need to share a line of action. So the forces need to share a line of action. So there are only two possibilities. These forces can be towards each other like this with the same magnitude, or they can be away from each other like this. Okay. If there is a third or more forces acting on this body, that ruins all of this. So the simplification that we're going to use is based on this assumption. And if you have more than two forces on a body, you can't use it. Okay? So this is only true for two force bodies. The two forces, when we put these things into structures, are going to be, there's going to be a joint at each one of these points, and there's going to be, reaction loads at each one of these 2 points. And so weight is enough to give you a third force on a body. And so anytime you're including the weights of a body, you can't use this truss simplification, which is obviously like limits when you can use this a lot, yes.
Could we use this for making close-ish estimates?
Yeah, so that's the idea, is that you use this truss simplification when the weights of the bodies are negligible compared to the other forces that are going to be applied. And examples of that are, like a bridge is a good example of that, the truss that supports a bridge. The weight of the concrete and the cars and whatever is a lot bigger than the weights of the members. And so, yeah, you get sort of a sense of what's going on with that as an approximation. So this is useful when the weights of the members are small compared to the external loads. And the other requirement is that the external loads all have to be applied at the joints. Because if you have reaction loads happening at the joints and you have applied external forces applied somewhere else, then that's a third force on, at least one of these bodies. So the external loads have to be applied at the joints. Okay, so let's see an example of how this can simplify things. Anybody have any questions about that before I do a problem? Yeah.
Can you use internal loads to create two separate sections of two forces?
No, because when we get to internal loads, you'll see that those internal loads include a couple. And so couples also cannot be, these have to be forces. You can't have couples in here either. Okay, so an example. So we've done problems like this a bunch of times. Let's say we have an isosceles triangle. like this. The lengths of the members are 1 meter. The angles that these make with the horizontal is 20 degrees. And let's say we have a 1,000 Newton horizontal external load applied at this pin. Okay, so if we were going to use just the full, as I've said a bunch of times, the approach that we've been using for structures can work for anything. It can work for this. We're neglecting masses. Ignore the weights. If we use the full approach, how many equations and how many variables would we get for this system? 6, yep, 3 for each body. I'll call that the full approach. Gives 6 equations for 6 variables. So I'm going to use the truss simplification. And the way I'm going to take advantage of this is we know that the forces just act along a line between the joints. Okay. And so I'm going to isolate, instead of isolating the members, I'm going to isolate the pins. And I'm going to assume the force on the pin is like a cable that can produce tension. That's if we get a positive value for this force, or compression. So cables can't do that. That's if this force comes out to be negative.
So is the idea behind that really just to make it only one variable per pin?
Yeah, exactly. Each pin has one force variable on it representing each member. So the members we're going to treat them as if they're cables, okay? And the only difference is we can get positive values, and with cables, we could get negative values, and with cables we would only get positive values. So I'm going to label these. I'm going to call that member 1, that member 2, and I'm going to call these joints A, B, and C. And I'm going to start with a free body diagram of B. It turns out in this one, this is all we're going to need. So here's the pin. And what loads are acting on this pin? Well, we're treating member 1 like it's a cable. So there's going to be a force, I'll call it F1, pulling on the pin that way. And member 2, we're going to pretend that's a cable. So there's going to be a force this way from body 2. And then that 1,000 Newton force is acting. And this is it. Okay? This pin we're going to treat like a particle. So we're only going to get 2 equations out of this. So Newton's second law says we have this force 1,000, 0. This force F1, that is going to be F1 times the cosine and sine of 200 degrees, you know. If you think of the coordinate system like this, this force F1 is like that, where this angle is 20 degrees. So to get from the x-axis to here, you get to 180, go another 20 for 200. Okay. And so cosine and sine of 200 is negative 0.940, and then negative 0.342. Any questions about that one? And then the force for F2, that one is this way, where this angle is 20 degrees. So you can do that as cosine and sine of 340 degrees or cosine and sine of negative 20 degrees, and you get 0.940 F2, negative 0.342 F2. That's all the forces, so this is equal to zeros. And you have a system of two equations for two variables. And notice that this gives us everything we want to know about this. That it gives us the tension or compression in F1 and the tension or compression in F2. So the first one says negative 0.940 F1 plus 0.940 F2 is equal to negative 1,000. And the second one says negative 0.342 F1 minus 0.342 F2 is equal to 0. And you can see, I mean, how when you're doing these calculations by hand, this huge reduction in the number of variables and equations is really valuable. It's pretty easy to just do this by substitution. This second equation says that F1 is negative F2. And so then you can plug this in and you get that negative 1.880 F1 is equal to negative 1,000. And so F1 is equal to, bless you, 531.9 newtons. And so F2 is equal to negative 531.9 newtons. The positive here means that kind of, so we're always doing this by assuming that these members are in tension. Positive means that that assumption was correct. So positive means this member is in tension. Negative means that our assumption was backwards, so it means that the member was in compression. And that makes sense if you look at this. You can imagine if these were made out of rubber, you'd be stretching member 1 with this force, and you'd be squishing member 2. Okay. Well, so this is a good approximation if these weights are small compared to that external force of 1,000 newtons. So if we said that the masses of those two members were like 1 kilogram each, something small, and we did the full calculation, we would get something close to this, but not exactly this. Okay.
Where's the line of the mass being too much?
Yeah, well, it's just a matter of how much precision you need. So let's do this problem now let's use 1 kilogram and see what it looks like. Okay. So how close is this approximation? So let's do the full calculation. For the masses equal to 1 kilogram. Okay, so free body diagram of member 1. Up at that pin B, the pin is part of member 1, so that 1,000 Newton force acts here. We also have the force on 1 by 2. We have a weight force down of 9.81. And here we have a reaction force RA. I'll put my about point down here at A. So the rho vector is zeros. Force vector is RAX, RAY. Cross product is 0. Then F12. Uh,
0.939.
Yeah, oh yeah, 1 meter long. Right, so that is, yeah, I'll call it 0.940, 0.342. The force vector is F12x, F12y. Cross product is 0.94 F12y minus 0.342 F12x. Then the 1,000 Newton force, same rho vector. The force is 1,000, 0. Cross product is negative 342. And then last is the weight force. That rho vector is half of this one. So 0.470, 0.171. The force is 0, negative 9.81. And and that cross product is negative 4.61. So equation 1 says RAX plus F12X is equal to negative 1,000. Equation 2 says RAY plus F12Y is equal to positive 9.81. And equation 3 says negative 0.342 F12X plus 0.940 F12Y is equal to positive 346.61. Everyone agree with me on those? Okay, and then member 2. Up at the pin B, that 1,000 Newton force is not applied to this. Bless you. So the only force we have here is negative F12. Then we have this weight force, 9.81. And then down here we have the reaction RC. I will put my about point here, I guess. So the force vector negative F12 has a row vector of 0. The force is negative F12X, negative F12Y, crosses 0. Then for RC, we have 0.940, negative 0.342. Force is RCX, RCY. Cross product is 0.940 RCY plus 0.342 RCX. And then the weight force, the row vector is half this one. So 0.470, negative 0.171. The force is 0, negative 9.81. And so you get negative 4.61. So equation 4 for our system is negative F12X plus RCX is equal to 0. Equation 5 says negative F12Y plus RCY is equal to positive 9.81. And equation 6 says 0.342 RCX plus 0.940 RCY is equal to 4.61. Okay, so we don't want to solve this by substitution, so here's the augmented matrix. We have 6 variables and 6 equations. I'll do it in this order. RA, F1, 2, RC, equation 1, we have 1 RAX, 1 F1, 2X, and negative 1,000. Equation 2, we have 1 RAY, 1 F1, 2Y, positive 9.81. Equation 3, we have negative 0.342 F1, 2X, positive 0.940 F1, 2Y, and then a constant of 346.61. For equation 4, F1, 2X's, we have negative 1. Our CX's, we have positive 1. Everything else is 0. Equation 5, F1, 2Y's, we have negative 1. Our CY's, we have positive 1. Constant is 9.81. Equation 6, RCX's, we have 0.342. RCY's, we have 0.940. And then the constant is 4.61.
Find the length.
So, well,
So like square root the squares.
oh, we could do that. I was going to go the other way, I guess, and I was going to multiply these by the directions, you know? So to compare, I'm going to turn the truss tensions and compressions into force vectors. And so in order to do that, I have to think about what's happening at those two joints with the ground also. So a free body diagram at RA. What's happening there? So we have for that pin at A, okay, we have two things going on. We have member 1 pulling on that pin, and then we have a force vector that's applied to that pin by the ground. Okay, so we have this with a magnitude of, what was that tension force? 531.9. So 531.9 pulling that way. And then we have this force RA that we're trying to calculate. And so Newton's second law says RAX RAY plus 531.9 times a unit vector in that direction is equal to zeros. And so RA is equal to negative 499.99, negative 181.91. Okay, so how close are we? You know, it's in the same ballpark, but it's definitely more than we ever get for round-off error in problems. And that's with a pretty small weight on that member. So this is the truss. We got negative 486.52, negative 172.10 for the full. You can, keep going through like that. But yeah, does it tell you anything useful to do this as a truss simplification in this case? Yeah, it definitely gives you an order of magnitude ballpark. But,
So I suppose
this is better.
If you were building a bridge using this, you could say, just throw an extra 50.
Yeah, right. I mean, I think that is sort of what you do. You calculate, you get an estimate, and then you incorporate a factor of safety into it. You say like, okay, let's make it twice this strong or 3 times this strong, and then we should be good. Yeah. Well, I do want to do a problem where you go through the truss calculation. Let's just wait until next time. And so, yeah, I want you to get used to doing this, do it a time or two, because you are going to see people, like, there will probably be a class or two where at some point they're going to say, like, solve this truss, and you should at least have some idea of what's going on. It's not something that, from feedback I've gotten from students at the U, it's not something you're going to be doing a lot, doing truss calculations, but you should sort of recognize what it is and how to do it. So, okay, that's all. Let's stop.
Probably more for civil, right?
Yeah, you would think so, but I just haven't heard of a lot of people doing it. I mean, like, the thing is, you wouldn't be doing any hand calculations really under any circumstances except in classes, no matter what area you're in. And a computer program would not need to use this truss simplification, so you just use sort of some version of like a full method. One thing, someone brought this up before. One thing that can be useful for a truss simplification is if you do have members that have very small masses. Sometimes you can incorporate the truss simplification into, like, just treat this, do the full method, but then for that one member, treat it like it's a cable that can produce tension or compression, and it cuts down a couple of variables. But anyways, we'll go through that next time.